Christian Cajochen put 33 volunteers in a windowless laboratory for 3.5 days. No clocks, no phones, no natural light, no moon. The participants had no idea what phase the moon was in outside. They couldn't have known. The laboratory was sealed underground, with controlled artificial lighting identical across every hour they spent inside. And still, when the moon outside turned full, their brains dropped into 30% less deep sleep. Their melatonin collapsed. They took 5 extra minutes to fall asleep, and every single one of them reported feeling worse the next morning. They didn't see the moon. They didn't know it was full. Their bodies knew anyway. Here is what the data forces us to confront. Before writing, before agriculture, before anything we'd call a calendar, ancient humans encoded a timekeeping system into their bodies that modern science still cannot explain. And that same system, silent and involuntary, is running inside you right now. The Cajochen study. In July 2013, Cajochen and his team at the University of Basel published their findings in Current Biology, and the paper landed like a provocation. The lunar effect on human behavior had been dismissed for decades as folklore, confirmation bias, superstition. People who claimed to sleep worse around the full moon were told they were imagining things, noticing only what they expected to see. The scientific consensus was clear. The moon does not affect human sleep. Cajochen's study was not designed to test the moon. He and his team had collected sleep data years earlier for an unrelated study on circadian rhythms and aging. 33 healthy volunteers, aged 20 to 74, had spent 3.5 days in a controlled laboratory with EEG monitoring, blood draws for melatonin, and strict light-dark protocols. The data had been sitting in storage. Years later, over a drink at a bar, not in a laboratory, not in a grant proposal, someone mentioned the full moon. Cajochen realized they could cross-reference their old sleep data with lunar phase. The study was retrospective. No participants had been told the moon was relevant. No researcher had mentioned it. The data could not have been influenced by expectation because nobody involved knew the question would be asked. Here is what the data showed. During the nights around the full moon, EEG delta activity, the electrical signature of deep, restorative NREM sleep dropped by 30%. Participants took an average of 5 minutes longer to fall asleep. Total sleep time decreased by roughly 20 minutes. Subjective sleep quality ratings dropped. And the blood draws showed a measurable decline in endogenous melatonin, the hormone that initiates and sustains sleep. The effect was not subtle. It was not marginal. It was a full-throated biological response to a stimulus nobody saw. Now here is where it gets strange. The Toba replication, with and without electricity. For 8 years, the Cajochen study stood as an intriguing but isolated finding. Skeptics pointed out that 33 participants in a Swiss laboratory were not representative. Maybe Europeans had some peculiar sensitivity. Maybe the artificial lighting protocol was contaminated. Maybe it was a statistical artifact. In January 2021, a team led by Leandro Casiraghi at the University of Washington published the replication that ended the debate. Casiraghi's team distributed wrist actigraphs, motion-sensitive sleep trackers, to 98 individuals across 3 Toba-Qom indigenous communities in the Argentine Formosa region. This was the critical design choice. One community had full access to electric light. One had limited access. One had none. If the lunar effect were merely a response to moonlight, brighter nights making sleep harder, then communities without electric light should show the strongest effect, and communities with electric light should show the weakest. The prediction was straightforward. The data said something else entirely. All 3 communities showed the same lunar pattern. Sleep was delayed and shortened in the 3 to 5 nights preceding the full moon, regardless of electric light access. The effect was actually slightly stronger in the community with full electricity than in the community with none. Moonlight was not the mechanism. Something else was driving the signal. Casiraghi's team concluded that the human sleep-wake cycle carries a circulunar component, a biological rhythm synchronized to the 29.5-day lunar month that operates independently of light exposure. It does not depend on seeing the moon. It does not depend on knowing the phase. It is endogenous, built-in ancient. The finding raised a question the paper could not answer. If the circulunar clock is real, and if it predates modern humans, what was it for? Why would evolution build a clock that tracks a celestial body and embed it so deeply that even artificial light cannot fully erase it? The answer is carved into a bone that predates writing by more than 30,000 years, the Lebombo Bone and the Aubry-Blanchard notations. The Lebombo Bone is not impressive to look at. It is a 13-centimeter section of baboon fibula, dark brown, weathered, found in the Lebombo Mountains on the border between South Africa and Eswatini. It could easily be mistaken for a random bone fragment by anyone who didn't know what they were looking at. It is approximately 35,000 to 43,000 years old. Carved into its surface are 29 distinct notches. 29 is not an arbitrary number. It is the whole number approximation of the synodic lunar month, the time from one full moon to the next. It is the same count that appears on the Ishango bone from the Congo, dated to roughly 20,000 years before present, and on the Aubry-Blanchard bone plaque from the Dordogne in France, dated to 28,000 years ago. When Alexander Marshak examined the Blanchard bone under a microscope in the late 1960s, he found something that changed the field. The notches were not made all at once. They were made with different tools, at different times, from different angles. Some were sharp and fresh. Others were worn from handling. The pattern suggested cumulative addition, mark by mark, day by day, over a period of approximately 2.5 lunar months. Marshak published his findings in Science in 1965 under the title Lunar Notation on Upper Paleolithic Remains. The paper was controversial. Some archaeologists argued the marks were decorative, random, or tally counts of hunted animals. But Marshak's microscopic analysis of the tool marks made one thing undeniable. These were not decoration. They were sequential records. Someone in the deep Paleolithic was tracking time, not with writing, not with numbers as we understand them, but with a physical notation system that mapped the moon. Here's the counterintuitive detail that separates this content from everything else. The Lebombo bone, the Ishango bone, and the Blanchard plaque were all discovered hundreds of thousands of kilometers apart, separated by thousands of years, in entirely different archaeological cultures. The 29-count notation system was not a single invention that spread. It was independently discovered, or independently necessary across continents and epochs, which means the moon was not just the first calendar. The moon was the first piece of natural infrastructure that humans everywhere, without exception, recognized as worth tracking. And the reason goes deeper than bone markings.